Chapter 5 is about magnetism. Section 1 is about the magnet and magnetic field and the source of magnetic field. We had two types of forces. We had contact forces and we had field forces. For the field forces, we need to have a field. We had gravitational field, which is the source of gravitational force, which happens between two masses and it is always attractive. And we had electric field, which was happening between two charges. If the charge is alone, we already have the field around it. If we have two positive charges, the fields will try not to touch each other, so they will change their directions. That's why we have repulsion between positive and negative and negative. The electric field in the positive is away from the charge, in the negative it is toward the charge. If we have a negative and a positive charge, we will have attraction between them because the electric field lines are in the same direction. The lines will be combined with each other. The last one that we will study in this section is called as magnetic field, which is the field that we have around a magnet. What is the source of magnetic field? The source of magnetic field is a moving charge. Again, the source of magnetic field is a charge, but the charge must be moving. Inside an atom, we have two types of movement of electrons. The first one is the spin of electron around itself, and the second one is orbiting of the electron around the nucleus. Both will produce a magnetic field for the atom. In some atoms, the electrons will cancel each other's magnetic field, but if the electron does not cancel each other, we will have something that's called as domain. The symbol of magnetic field is capital B. It is a vector quantity. The unit is Tesla. When we have a group of atoms that have a magnetic field, they will come together and their magnetic fields will be in the same direction. They will produce a domain which is called as magnetic domain. We have three types of materials. The first one is called as non-magnetic materials. It is the materials that have no magnetic field. And they cannot be magnetized either because there is no produced domain, so they don't have any domain at all. So no domain is formed in the non-magnetic materials. The second type of the material is magnetic materials, which are the materials that can be magnetized, and they will be called as ferromagnetic materials. In ferromagnetic materials, we have domains. Here, each domain has magnetic field, but all of the magnetic fields are randomly oriented and they all cancel each other. As a result, the net magnetic field is equal to zero. Examples for ferromagnetic materials are iron, cobalt, and nickel. The third type is a magnet itself. In a magnet, we also have domains. Each domain has a magnetic field. The difference here is that the magnetic field of the domains are all in the same direction. The more domains or the more alignment you have, the stronger the magnet will be. So we'll have a net magnetic field that is greater than zero. This is a piece of iron before exposing it to a magnet or magnetic field. And let's have a magnet. One side is north, one side is south. The direction of the magnetic field is always coming out from the north pole, which we'll be talking about it in a minute. This is the direction of the external magnetic field or the magnetic field of the magnet. As we insert this iron inside this field, it will realign all of the randomly oriented magnetic domains. The iron becomes magnetized. The magnetic field of the iron will be greater than zero. The randomly arranged domains become regularly arranged and the iron becomes magnetized. After removing this, would the iron go back to being non-magnetic right away? Of course not. The iron will retain some of its magnetization for some time. This is called as magnetic hysteresis. The magnetic flux density increases non-linearly with the increase of the applied field. So if we increase the applied field, the magnetic field of the iron will increase. Every nonlinear graph will produce a curve, and this curve is called as hysteric curve. Every magnet has two poles, and if we break a magnet into two pieces or any pieces, each piece will have two poles. If we have some iron fillings or iron powder and spread it on a magnet, the iron fillings will become aligned in the same direction as the magnetic field of the magnet. So they will take the shape of the magnetic field of the magnet. It will form a pattern. If we trace this pattern, the magnetic field lines will look like that they start from a pole and end at another pole. But in reality, magnetic field lines continue within the magnet. So magnetic field lines have no beginning or end because they form closed loops. Since magnetic field is a vector quantity, we need to give it a direction. The magnetic field lines will be coming out from the North Pole and they will be entering the magnet from South Pole. Direction of the magnetic field outside of a magnet is always from north to south because it's coming out from the North Pole. And inside the magnet, it is always from South Pole to North Pole. The direction of the magnetic field can be found by using a compass. A compass is a magnetic needle which has North and South Pole that can rotate. When we enter this compass into a magnetic field, the needle will rotate until it has the same direction as the external magnetic field. Let's have a compass, an external magnetic field. Let us put this compass into this field. As you see, the direction of the magnetic field of the compass and the external are not same. The needle will rotate until it has the same direction as the external field. Change this one. From now on, we need to work on and study on three planes. We will have three axes. The first one is using paper, which is called as page. So let's draw vectors on a paper. If the vector is to the right, draw a vector that is to the right. We will call this as right to the page. If it is to the left, draw a vector that is to the left of the page. If it is up, draw a vector that is up to the page. If it is down to the page, draw a vector that's downward, so it will be down to the page. These four vectors are parallel to the page itself. They will be called as in the plane of the page. If we have another vector that is not parallel to the page, vector had a tail and a head. So if the vector is moving toward you, you will be seeing the head of the arrow. It will be coming out of the page. If you look at the page, the symbol will be dot because the head that you see will look like a dot. If the vector or the arrow moves away from you, you will be seeing the tail, which will go into the page. If you look at the page, the tail will have a shape of X. So X will be symbol of into the page. Note that into the page and out of the page are perpendicular to the plane of the page or perpendicular to the page itself. X, Y, Z coordinate plane, they are all perpendicular to each other. We can connect it with the first one and say that X is to the right, Y is up, minus Y is down, and minus X is left, plus Z is out, and minus Z is into the page. But please remember, if the question gives you the quantities in terms of X, Y, and Z, your answer must be in terms of X, Y, and Z too. The third one is using the geographic directions. If you face north, so in front of you will be north, your back will automatically be south, your right hand automatically will be east, your left will be west, and above you will be up to the sky, below you would be down to the ground or toward earth.
The last topic in section 1 is magnetic flux. Magnetic flux is defined as the number of magnetic field lines that crosses a given area in the normal direction. So this is important. The magnetic field lines must pass through the area perpendicularly in order to have a magnetic flux. And the unit of magnetic flux is Weber, which is WB. Let's have an area and some magnetic field lines. So as you see in the picture, we have 5 magnetic field lines that are passing through the area. So we can say that the flux here is 5 Weber. Magnetic flux depends on three factors. The first one is the magnetic field itself. As magnetic field increases, magnetic flux also increases. Let us have two examples. In the first one, we have 5 lines that are passing through the area, so we have a strong field. In the second one, we have a weaker field. In the first part, magnetic field of A is greater than magnetic field of B. So clearly the flux in A will be greater than flux in B. The second point that flux depends on is the area of the surface or the plane or the loop. As we see, the first area is bigger. So we have more number of lines that are passing through this area. So a greater area will give us a higher or a more flux. So as area decreases, flux also decreases. Before talking about the third point, we need to find another vector which is called as area vector. An area vector is a vector which has a magnitude that is the area that you have studied until now. But since this is a vector, it must have a direction, and its direction is always normal to the plane or the surface. Normal means perpendicular. Let's have a box or a cube. Each side of the cube faces a different direction. For example, this side is facing left, this side is facing up, and this side is facing down, this side is facing the right side. Each side has its own direction. We can say that each side is facing a different direction. So from now on, when we draw n, it means it is the direction of the area vector. The third point talks about the orientation of the surface or the plane with respect to the magnetic field. And here we have three cases. When the plane or the loop is perpendicular to the magnetic field and this loop is facing the right side, so the area vector or the normal will be also to the right. Some magnetic fields are passing through this area, the loop or the plane perpendicularly. So the normal and the loop are parallel to each other. So if the plane is perpendicular, the normal is parallel. And we need the angle between normal and the field all the time. So the angle between them is equal to 0. The second point is if the plane of the loop is parallel with the magnetic field, again the area is facing the right side, so the normal is also to the right. This time the magnetic field lines will be downward or upward, and as you see they are parallel to the plane of the loop. But since they are parallel to the plane of the loop, they are perpendicular to the normal, and the angle between the normal and the magnetic field will be 90 degrees. In the first part, since all the lines are crossing the area perpendicularly, flux is maximum. But in the second part, none of the magnetic field lines are passing or crossing the area perpendicularly, the flux is 0. In the third case, if the plane is tilted, again the area is facing the right side, so the normal will be to the right side. The magnetic field is making an angle. Theta is between normal and the field. And this magnetic field has two components. One of them is sine, one of them is cosine. The one that is attached to theta is always and always cosine. And the one that is not attached to theta is always and always sine. Now, which one of these components are passing through the area? Of course, the cosine component. So the cosine component is crossing the area perpendicularly, but the sine component does not cross the area at all. As a result, the one that's creating the flux for us is the cosine component, and the one that's not creating flux is the sine component. When we write the equation for the flux, which is equal to A dot B, in physics we have two types of product, a cross product and a dot product. A dot product gives us a result that's always a scalar quantity. So magnetic flux is a scalar quantity, which will be equal to AB cosine theta. And the cosine component is creating the flux. The unit of magnetic flux was Weber. So Weber is equal to Tesla times meter square. Tesla is because we have magnetic field here. Meter square is because of the area.